Okay, very good morning, all of you. Okay, and now we are going to start the push-pull amplifier, and we'll discuss the operation. So I have already mentioned that it will provide 180 degrees out of phase. Okay, so here the only thing is we have to remember whether you are applying a positive half cycle, so it should be positive and it should be negative. So then what happens? What happens? Only one transistor will be
on and other Q2 will be off, sir.
yes. That's right. One transistor will be on, another transistor will be off.
Off, sir.
Okay.
Green shift.
Oh, sorry. Wait a minute. So I think that everyone is having a circuit. Okay. Now it is visible?
Yes, sir.
Yes, sir. So whenever we have applied a positive half cycle, what happens is here it is a positive, other one is a negative terminal. So obviously one transistor will conduct, other one will be
non-conducting.
Yes, right. Whenever we have applied a negative half cycle, so what happens? Q1 off, Q2 on.
Q2 on, sir.
Okay, all of you understood?
Yes, sir.
Yes, this is the operation. Okay, and coming to the how the waveforms will be changed, I think. For example, if we have applied if we applied a full, this is the input we are giving. Okay, so one transistor will conduct, means that let us consider Q1 is on initially, the Q2 is off. So means that which is high, which is low. So Q1 is having the current called IC1. All of you understood?
Yes, sir.
Okay. So Q2, there is no current. So here it is 0. So means that how we are going to draw the waveform?
Positive half cycle.
Positive half.
So we will get the positive half cycle only. Okay, so this is the input and this is considered as IC1. What about the second one? Second case, if you apply a negative half cycle.
Q1 0, Q2 IC2.
IC1 equals to 0.
So what happens? This is IC2. All of you understood?
Yes, sir. Understood, sir.
What about IL? IL should be the combine of
Both IC1 and IC2.
yes, combining the outputs here. Okay. So finally, the current IL is equal to I1 minus I2 or IC1 minus IC2. So all of you understood?
Yes, sir.
Yes, sir.
I think all of you got the what is the change we have observed.
Yes, sir.
Yes, sir.
Yesterday and today. Okay.
Yes, sir.
Okay, sir.
Okay, sir.
Shall we go to the analysis?
Okay,
Okay,
sir.
sir.
Okay.
Yes, sir.
Okay, okay. What we have to do when we are going to the analysis? What is our first point? Hello.
Sir.
To do the analysis, what we have to do? What we have to identify first?
On first half cycle, one of the transistor conducts and other remains off, sir.
Okay. What is Q point for class B?
VCE color 0, sir.
Comma 0.
Huh?
VCE,
VCE,
0.
comma 0.
So
Comma
VCE
0.
Q comma 0.
0.
Is it right?
Yes, sir.
Yes,
Yes.
sir.
Yes, sir.
So we have to calculate DC power input. How to calculate DC power input? So here each and every transistor, either it may be a Q1 or it may be a Q2, providing half wave rectifier output. Is it right or not?
Yes, sir.
So how to calculate power? So here the current is IDC. Okay, voltage is
VCE.
VCE is
VCE.
nothing but VCC.
VCC.
If you apply KVL at the collector terminal, you will get VCE is equal to VCC. Okay.
Okay,
Okay,
sir.
sir.
So how to calculate IDC? Here the actually what is IDC? Average current. Is it right or not?
Yes, sir.
Yes, sir.
Average
Sir.
current in the transistor. But here what happens? Here it is completely operating like just like full wave. Is it right or not? Hello.
Yes, sir.
So how
Sir,
many number
half.
of transistors? Let's tell me. 2. Okay, 2 into what is the average current? Im by pi.
5.
What is the average current? 2 Im by
5.
pi. All of you understood or not?
Yes, sir.
Yes, sir.
Or simply you may have to say that, sir, we are getting the output as, what is the output we are obtaining as full wave output? Is it right or not? At the RL.
Yes, sir. Correct.
Yes, sir.
What is the average current for full wave?
IM by pi.
2 Im by pi. Is it right or not?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Now what we have to calculate? Power. PDC is equal to, what is the formula?
VCC into IDC, sir.
VCC into IDC. Right. So what is IDC?
2 IM
2
by
I
pi, sir.
2m by pi. Now we can write this one as 2 by pi VCC multiplied by IM. This is the DC in power. All of you understood?
Yes,
Understood,
Yes,
sir.
sir.
Now we have already assumed in the last in class A transformer coupled power amplifier also the internal resistances of winding. Assume that resistances of winding to 0 ohms, right? Hello.
yes, sir.
Then what happens? VCEQ is equal to VCC. So directly we can write the Q point VCEQ comma ICQ is equal to, what is Q point here? VCC comma 0.
VCC, 0, sir.
All of you understood?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So now we will enter into the AC operation. What about AC operation? Here the Q point is at, this is the Q point. What is the Q point here? VCC comma 0.
0, sir.
Okay. Then draw the load line, AC load line. What is the slope here? Minus 1 by, already we discussed, and hello.
Sir. Minus
Sir.
1 by RL.
And what about DC load line? What about DC load line? DC load line is
1 by RL.
Then what happens? Slope is minus 1 by RL. We assumed that here resistances are
0.
0.
0.
Then so there is no slope here.
Line, sir.
There is no slope.
Infinity.
So obviously, which is a
Straight line.
straight line. All of you are following.
Yes, sir.
Yes, sir.
Okay. So how we can draw the waveform? Here Q point is at 0. PCC comma 0. Then identify. At a time we are applying only one half cycle. Is it right or not? So which is I maximum, current represented as IM. Okay, here the waveform is. So then what is the amplitude of this? Vm. So which is V minimum. All of you understood?
Yes, sir.
Yes, sir.
Then what happens? Here the transistors only we are using either upper side or lower side. Is it right or not? Hello?
Yes.
Yes, sir.
Yes, sir.
If Q1 conducts, lower half cycle of the primary transistor, there is no current. If you use Q2 conducts, what happens? Upper half of the primary doesn't carry any current. So what happens? How many terms current will be, how many times current will be carried out? How many number of turns? That is depends upon the number of turns of the primary winding. Okay, let us consider number of turns n is equal to, what is the formula? N2 by N1.
1.
So the load we can consider, the primary winding resistive load is represented as RL dash. Okay. At the secondary winding load by N square. All of you understood or not?
Yes, sir.
Yes, sir.
Yes, sir.
Now calculate the AC power output. Calculate AC power output. What is PAC? Output is equal to, we can write which is an AC. So obviously the notation may change. PRMS multiplied by
IRMS,
Yes,
sir.
IRMS. What is the value of ERMS?
VM by root 2.
VM by root 2. What about IRMS?
IM by root 2.
IM by root 2. So the final value for PAC is
VM IM by
VM by 2.
by 2.
All of you completed up to now?
Yes, sir.
And we can substitute in the place of IM. So I is equal to V by R, right? Hello.
Yes, sir.
Yes,
So
sir.
yes, here the IM. So the notation will change for voltage also, which is VM. Okay. At the primary winding, what is the resistance here? RL dash.
RL.
Okay, substitute in place of IM. So VM by 2 multiplied by VM by RL dash.
RL dash.
So we can write this one as VM square by 2 RL dash. All of you understood?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, this is the PAC output. And if you want to write in terms of current, then what is the value?
IM
IM
square
square by 2 into RL dash.
Yes, IM square by 2 into RL dash. All
RL
of you
dash.
understood?
Yes,
Yes.
sir.
Yes, sir.
Okay. What is the next component? What is the next parameter?
Efficiency.
Efficiency, right? Efficiency is equal to, efficiency represented by eta is equal to PAC by
PDC.
PDC into 100.
Into 100.
200.
What is PAC?
IM
VM
by
IM by 2, sir.
VM IM by 2.
So PAC is nothing but VM IM by 2. What is PDC?
2
2 by
pi
pi
2
into
VCC.
2 IM
IM
by
into
pi
VCC.
multiplied by
into
VCC. Into
VCC.
100. Now what happened? IM both were
cancel.
cancelled. Now what is the final value?
VM pi by
VM by
VM
VC.
VM pi by
4
4
4
VCC
VCC into
100.
100. So we can write simply as pi by 4 multiplied by VM by VCC into 100. All of you understood?
Yes, sir.
Yes, sir.
Yes, sir.
What is the next parameter? What is the next?
Maximum efficiency.
Maximum efficiency. So maximum efficiency. So maximum efficiency. So we have to calculate percentage of eta maximum is equal to PAC by PDC into 100. So already we got the value as pi by 4 multiplied by VM by VCC into 100. Okay, here the what is the maximum value VM? What is the maximum value VM?
VCC.
Yes, very good, very good. The maximum value here is VCC. All of you understood?
Yes, sir.
Yes, sir. Yes, sir.
1 minute, I will show the. Yes, here this is V maximum, VM. So this complete VM is nothing but represented with VCC. All of you understood?
Yes, sir.
Yes,
Yes,
sir.
sir.
This is from, yes, this one as VCC equal to VM. Now substitute VCC in VM.
5 by 4 into 100.
Final value. What is the maximum efficiency? So if you substitute it, then pi by 4 multiplied by VM is nothing but VCC by VCC into 100. VCC cancelled. Then pi by 4 into 100. What is the efficiency?
78.5.
78.5.
78.5% of efficiency for push-pull
Class B amp.
Class B power amplifier. Okay.
Okay, sir.
Now
Yes.
power dissipation. Next parameter is power dissipation. How to calculate power dissipation? PD is equal to
PDC minus
by
PS.
PDC minus PAC. PDC is nothing but 2IM by pi multiplied by VCC minus PAC is nothing but VM IM by 2. All of you understood?
Yes, sir.
Yes, sir.
Now substitute, we know already IM is equal to VM by RL dash.
RLS.
Then
2 into
2
Vm by
into VCC by pi multiplied by Vm by RL
RL
dash
dash
minus
minus
Vm
Vm
by
by
2
2 into
multiplied
Vm
by
by RL
Vm by
dash.
RL dash. Now expand 2
Vm
by
by
pi
RL.
into VCC Vm by RL dash minus Vm square by 2 RL dash. All of you understood?
Yes, sir.
In class A power amplifier, the power dissipation is considered, or power dissipation is maximum when the input signal is present or absent.
Absent.
Absent means that without having any input signal, there is a power dissipation because of DC. That's what we already discussed in class A, right?
Yes, sir.
Yes, sir.
But in class B, if the input signal is 0, then power dissipation is so input signal is nothing but here let us consider Vm is 0. Then what happens?
Power dissipation becomes 0.
So means that power dissipation is not maximum. Is it right or not?
Yes,
Yes,
sir.
sir.
So it is 0. So compare with class A power amplifier, class B push-pull amplifier is better in terms of efficiency as well as power dissipation. All of you understood?
Yes, sir.
Yes, sir.
What is the next parameter? Maximum power dissipation. Maximum power dissipation. So how to calculate maximum power dissipation? So what is the value we have obtained in power dissipation? 2 by pi multiplied by VCC Vm by
RL
RL
dash
dash
RL dash minus
minus Vm square by
by
2
2
RL
into
dash.
RL dash. So we are mentioning that if the input signal is 0, the total value is 0. So PD maximum is equal to 0. Is it right?
Yes, sir.
Yes, sir.
Okay. Now what we are going to do is here we'll apply the differentiation for this expression. Let us consider as 1. Apply the differentiation in equation number 1 with respect to Vm. And now tell me what is the dPd by dVm is equal to
2 by pi into VCC by RL dash minus
2 by pi into VCC
VCC
by RL dash.
RL dash
So that is
minus
Vm is
2
1.
into
Okay, minus
2 into
2 into Vm by 2 RL dash. Is it right?
yes, sir. 2 cancel.
Sir.
Here in class B power amplifier, we will obtain the maximum power dissipation by differentiating the PD with respect to the Vm. Now tell me 2 cancelled. So 2 VCC by pi
Pi
into
RL
RL dash minus
minus
VM by
VM by RL dash.
so you are saying that power dissipation is 0, then dPd by dVm is equal to 0. Then what happens? So 2 VCC
Equals
by
to
pi into RL dash is equal to
VM
VM
by
by RL.
RL dash cancel.
RL dash cancel.
VM is equals to 2 by pi
VM is
VC.
equal to 2 VCC by pi. All of you understood?
Yes, sir.
So this is the condition for maximum power dissipation.
Power dissipation.
Yes, right. Very good. All of you understood?
Yes, sir.
Okay. Now assume that this is as 2. Substitute Vm, that is 2, in equation number 1. Now what is the equation number 1? PD maximum is equal to 2 VCC by pi RL dash
Minus
multiplied by Vm is nothing but 2 VCC by pi minus Vm square. Vm square is nothing but 2 VCC by pi whole square into 1 by 2 RL
1
dash.
by 2.
All of you understood?
Yes, sir.
Yes.
Yes, sir.
Now we can express this one as 4 VCC square by
Pi square RL dash
pi square RL dash
minus
minus
4 VCC square by
4 VCC square by pi square
2 RL dash.
2 RL dash.
2 pi square RL dash. 2 times. So then
2 VCC square pi
we can write
pi
4 by pi square
RL dash
VCC square by RL dash minus 2 by pi square
into
VCC square by
RL dash. 2 by pi square into VCC
yes.
square by RL dash.
If you make the common as
VCC square by RL dash.
VCC square by pi square RL dash. VCC square by
pi
Pi
square
square RL
pi
dash.
square RL dash. So it is 4 minus 2. Then
2
we will get
VCC.
the 2 by pi square multiplied by VCC by RL dash. All of you obtained VCC square by RL dash. Hello.
Yes, sir.
Yes, sir.
Sir.
All of you understood?
Yes, sir.
Yes, sir.
Now tell me at Vm is equal to VCC for the maximum condition. That's what we considered earlier, right?
Yes, sir.
Yes, sir.
Yes, sir.
Sir.
That is at where we considered PSE maximum. Is it right?
Yes, sir.
Yes, sir.
Yes, sir.
So when we are writing PD maximum, if you want to write, for example, what is the PD maximum now?
2 by pi square into
2 by pi
PD
square
maximum is
square by
equal to
RL dash.
2 VCC square by
Pi square RL dash.
pi square RL dash. So I want to write this one as 4 by pi square into PAC maximum. Shall we write like this? What is PAC maximum?
2 Vm square by RL dash.
Vm square is nothing but. So we will get VCC square by 2 RL dash.
Yes, sir.
Shall we write like this?
Yes, sir.
So all of you understood?
Yes, sir.
Okay. So whatever the power dissipation, whatever the efficiency we have considered for the both transistors, right? Hello.
Yes, sir.
Sir.
If you want to calculate power dissipation for or maximum power dissipation for each transistor. So what is not, this is nothing but PD maximum per transistor. So we can write this one as PD maximum by 2. Will you agree?
Yes, sir.
Yes, sir.
What is PD maximum? 4 by pi square into PAC maximum by 2.
2 by pi square.
2 by pi square PAC maximum.
max.
So all of you understood?
Yes, sir.
Yes.
All of you understood the power dissipation?
Yes,
Yes.
sir.
Yes.
Yes, sir.
Okay. And now we are going to move on to the harmonic distortion. How to calculate harmonic distortion here? Here both the currents are sine waves or cosine waves?
Sine waves, sir.
Sine waves or cosine waves? Base currents.
Cosine. Sir.
So both the base currents are cosine waves. So we have to represent the base current. For example, IB1 is equal to, we can represent this one as IBM multiplied by, which is a cosine waveform, obviously cos omega t. All of you understood?
Sir.
Hello.
Yes,
sir.
sir.
So output current of the transistor 1. So output current is at the collector. So obviously which is IC1 is equal to, how we have to represent the harmonic distortion? What is the initial current? ICQ ICQ plus, hello,
V0 plus V1 cos omega t plus
B0 plus
B2.
B1
B1
cos
cos omega t
cos omega t plus
plus
plus B2 cos 2 omega 2.
cos 2 omega t, if you want to write, plus B3 cos 3 omega t plus so on. All of you understood?
Yes, sir.
Yes, sir.
What about the input signal for second transistor? This is at Q1, at Q2. So IB2 is equal to, this is for negative half cycle. So we can represent with minus IB1. So minus, what is IB1? We can write this one as, I'm going to write, expand this one as IBM cos omega t plus pi. All of you agreed?
Yes, sir.
Here why IB1 I have written is, again it is a cosine waveform. Okay, that's why I have written as IB1. Or otherwise if you want to write again IBM cos omega t. All of you understood?
Yes, sir.
Yes, sir.
To eliminate the minus, I have written it as IBM cos omega t plus pi. Understood?
Yes, sir.
Yes, sir.
Now, how we can write IC2? Output current at the transistor 2. IC2 is equal to, again, harmonic distortion, DC. ICQ plus B0 plus B1 into cos omega t plus pi
Plus pi.
plus
Plus
B2 into
cos 2
B2 cos
cos 2 omega t
2
plus pi
omega t plus pi
plus B3 into cos 3 omega t plus pi plus and so on. All of you understood?
Yes, sir.
Yes, sir.
If we expand this ICQ plus B0, now I want to come back to negative. Okay, so I am expanding the cos omega t plus pi. So obviously we'll get the minus 1. So minus B1 cos omega t plus B2 cos omega t minus
Minus B3 cos
B3 cos
omega
3
t.
omega t. So this is 2 omega t, this is 3 omega t. Plus and so on. All of you understood?
Yes, sir.
Yes, sir.
So here IC1 as well as IC2 both are in same directions or opposite directions? Both are in opposite directions. So the total current I is equal to I1 minus I2 multiplied by coefficient K. Here the I1 is nothing but IC1 minus IC2. All of you understood?
Yes, sir.
Now you can substitute IC1 and IC2. Then what is the final value? K into, what is IC1? You just only consider 3 terms up to B3, okay? ICQ plus B0 plus B1 cos omega t plus B2 cos omega t plus B3, sorry, cos 2 omega t plus B3 cos 3 omega t.
3 omega
Minus, now tell me,
q plus B0
minus ICQ minus B0 plus
plus
B1 cos omega t minus B2 cos 2 omega t plus B3 cos 3 omega t. Now B0 cancelled. ICQ cancelled. Any other terms to be cancelled? B2
2
cancelled.
cos 2 omega.
That is also cancelled. So now we can expand this as, sorry, we have to optimize this as K into 2B1 cos omega t plus 2B3
Cos 3 omega.
3 omega t. All of you understood this step?
Yes, sir.
Yes,
Okay,
sir.
move the 2 to the outside. So 2K into B1 cos omega t plus B3 cos 3 omega t. You can write this and so on. All of you understood?
Yes, sir.
Yes, sir.
So what happens from the above expression? Whether the two transistors are identical or not. So the circuit is balancing the even harmonics. Is it right or not? Hello?
Yes, sir.
Now tell me, there are no even harmonics in the output. So which is called as half wave symmetry. If it is a full wave symmetry, it should be even harmonics as well as
Odd harmonic.
odd harmonics. But here it is removing or it is suppressing the even harmonics. Okay, so that's why this is called it as half wave symmetry or mirror symmetry. This is called as half wave symmetry or mirror symmetry. All of you understood up to this?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
Now write down the advantages. What are the advantages? Hello. What are the advantages?
Efficiency more than class A power amplifiers.
Okay. The power dissipation is 0 if there is no input signal. Is it right or not?
Correct,
sir.
sir.
What about impedance matching? Impedance matching is achieved or not? Hello.
Sir.
Impedance matching is achieved or not?
Yes, sir.
Impedance matching is achieved because of second transformer. What we have done in transformer coupled class A? What is the advantages? Hello.
Impedance matching to transfer more power.
Yes. So here also impedance matching is achieved. And the one more advantage is the circuit which is suppressing the even harmonics, that circuit is having, or that circuit provides output with less distortion. All of you understood? The circuit which suppresses the even harmonic component, that circuit is called as active device. Active device is nothing but which is having a less distortion. All of you understood?
Yes, sir.
Yes, sir.
Okay.
Sir, sir, repeat చేయండి sir.
ఏంటి ఈ పాయింట్?
Yes, sir.
The circuit which suppresses the even harmonic components or even harmonics. Okay, that circuit is called as active device. So all the active devices which are having very less distortion.
Okay, sir.
Okay, what are the disadvantages? The main disadvantage is how many transformers are required?
Two center tapped
Two
transformers.
center tap transformers are required. That is the one of the disadvantage. The circuit becomes complex or not?
Complex,
Complex.
sir.
Yes, sir.
Complex, heavier, okay, and costly also. Frequency response is poor. Frequency response is poor. Okay, all of you understood?
Okay, sir.
Please
Understood,
revise
sir.
the entire analysis. We will be back in 5 minutes. Okay?
Okay, sir.
I think you understood the 2 hours continuously.
Yes,
Hello.
sir.
Yes, sir.
Take a break for 5 minutes.
Okay, sir.
Okay, sir.
Okay. Thank you.
Okay.
Okay, shall we start?
Yes, sir.
Okay.
Yes, sir.
And the next type of power amplifier is complementary
Symmetry, push pull class.
symmetry
Push amplifier.
push pull
Power amp.
class B power amplifier. Okay. So this complementary symmetry push pull class B power amplifier is proposed to overcome the drawbacks of the push pull class B power amplifier. All of you understood? What are the disadvantages in push pull power amplifier?
Center tap transformers.
Yes, it requires two center tap transformers and which is expensive, and we have to provide two out of phase signals, right? With phase angle of 180 degrees.
180.
Yes, to overcome these drawbacks, this complementary symmetry push pull class B power amplifier is proposed. So why, which is called as a complementary? In this
ఆపరేషన్ కంప్లీట్లీ ఆపోజిట్ గా ఉంటుందేమో సార్.
లేదమ్మా లేదు. In this we are using one NPN transistor, one PNP transistor. So that's why which is called as complementary. Why symmetry? Both are manufactured with same material. Both are manufactured with same material. All of you understood? Hello.
Sir.
Yes, sir.
Okay, that's why which is called as a complementary symmetry push pull amplifier. And in this power amplifier they are completely avoided the transformer. Completely avoided the transformer. So now shall we draw the circuit?
Yes, sir.
Yes, sir.
All of you please draw the circuit. And all of you try to remember that whenever we are drawing a transistor, whenever we are drawing a transistor, we should have to draw with the circle only. Okay. Hello.
ఓకే సార్.
If
Okay,
any,
sir.
if anywhere
sir.
I forgot, plus you just do that. Okay.
ఓకే సార్.
One is NPN, the other one is PNP. All of you, please draw this diagram. All of you are completed.
Yes, sir.
Yes, sir.
Okay, what is the difference you observed from the previous circuit? What is the difference? We changed the another transistor as NPN to PNP, right?
Yes, sir.
Yes, sir.
Okay. And we have provided second transformer as T2 at VCC we have provided in the previous circuit. Is it right or not?
Yes, sir.
But here we are providing for the each and every transistor we are providing VCC1 and VCC2. Okay.
Yes, sir.
Yes, sir.
So previously what we have done is we have done 180 out of phase. For that we used the transformer 1. But here we simply changed the transistor from NPN to PNP. So no need of transformer at the input side. Is it right or not?
Yes, sir.
Correct,
So
sir.
directly we have applied a sinusoidal signal. So now can you explain the operation? I think you can easily explain the operation. For the positive half cycle. చెప్పండి. For the positive
NPN
half
trans
cycle.
Sir, for
Which one is on?
Q1 is on, sir. Q2 is
off. So current flows through RL is positive or negative?
positive.
Positive. Okay. Whenever we have applied a negative half cycle.
Q1 is off and Q2 is on, sir.
Q2 is on. Okay, whatever the current which is available at the RL. So For the complete cycle of the input, we are getting the complete cycle as output or not?
Yes,
Hello.
sir.
Sir.
Hello. Hello.
Sir.
Yes, sir. Complete full
Sir.
cycle వస్తుంది, sir.
Somebody is asking, please. Hello. Okay. So means that whatever the input we are giving as a full cycle, we are getting the output also for the full cycle. Is it right or not?
Right, sir.
Yes.
Right.
And one more thing is, here the R1, R2 are providing voltage divider network for Q1, and R3, R4 is providing voltage divider network for Q2. Is it right?
Yes, sir.
Yes. Yes, thank you. So what is the difference for the previous one and this one is only we are removing the transformers and we change the transistor. So there we are using the transformer, because of that we have used the RL dash
180.
for the primary winding. Is it right or not? Hello.
సార్
Yes, sir.
దానికోసం 180 degrees ఫేజ్ షిఫ్ట్ కదా సార్ వాడాము.
అవునండి, at the same time we have considered the load resistance for the primary winding as RL dash, right?
రైట్ సార్.
Yes. So here there is no RL dash and nothing. Simply make that RL dash as RL. The complete analysis is same as previous one. The complete analysis is same as previous one. All of you understood?
Yes, sir.
Okay, no need to calculate again. Okay, simply change the RL dash as RL.
Okay, sir.
Okay, sir.
Okay, all of you understood?
Yes, sir.
Yes,
Okay,
sir.
please again do calculate for all the parameters. Okay, that is your work. Okay,
Okay, sir.
if you have any
Yes.
doubts you may ask. Okay.
Okay, sir.
Yes, sir.
What are the advantages of this power amplifier?
Easy to construct.
Easy to construct, size is less,
Cost is less.
What is reduced?
cost is less, and transformer less. Frequency response will be improved or not?
Improve,
Frequency
sir.
response will be improved. What is the disadvantage?
2 voltage supplies,
Yes,
VCC1
right.
and VCC2.
Yes, that is the one of the disadvantage. And one more thing is the new term called crossover dissipation. Do you know about crossover distortion? Do you know about crossover distortion?
No, sir.
So means that, for example, if you use a germanium material, no need of crossover distortion. Why? Because for less voltage, the junction will be conducted. Is it right or not?
Yes, sir.
For silicon transistor or for silicon material, so it has to wait to break the junction up to
0.7.
0.7.
0.7. So up to that, is there any signal?
No.
No, sir.
No. So means that what happens? For example, sorry, 1 minute. For example, this is the sinusoidal waveform, right? Hello.
Yes, sir.
For the corresponding current, what we will do is simply we will consider this one and this one or corresponding voltage to draw. Okay.
Okay, sir.
But if you use the silicon material, so when it will start, it may be at 0.7, maybe at that position. So here also. Then what happens? Whether the distortion is available or not. Hello. Hello.
Sir, can you repeat, sir?
Sir.
I will write again. Consider this is a sinusoidal waveform, right? The transistor Q1 or Q2 conducts when base emitter junction should break. Is it right or not? Hello?
Yes, sir.
Yes,
Okay.
sir.
To break this particular base emitter junction, if the germanium, no need. Why? Because very less distortion because of the low cut-in voltage, 0.2 or 0.3, it is the cut-in voltage. But if you use the silicon material,
0.7.
0.7 means that you have applied the input signal, but where it conducts might be here. All of you understood?
Yes, sir.
Yes,
So at
sir.
the same time here on. So we have to consider the input signal with respect to these points.
Okay, sir.
Okay, sir.
Then what will be happen? Then what will be happen?
Some
The signal
Signal
is,
will be generated in between the two lines, sir.
yes, that is called as dead band. That is called as dead band.
Dead.
So at the same time for the negative half cycle also at somewhere like this. What happens again? All of you understood. So this is called dead band. Obviously the distortion will be takes place. Okay, this is called it as crossover distortion. This is
Okay,
called
sir.
as crossover distortion. All of you understood?
Yes, sir.
Why it is
Yes,
called
sir.
as crossover distortion? It occurs in between the function of the two junctions. Is it right?
Yes, sir.
Yes, sir.
If you apply one more positive half cycle, then what happens? Again, this point. So again, what happens? There is a distortion. I hope all of you understand.
Yes, sir.
Yes,
Okay, this
sir.
is called it as crossover distortion. Okay. Now, what are the differences between or compare push-pull class B and complementary symmetry class B? In push-pull class B, either we may have to use only one type of transistor, either NPN or
PNP.
PNP. In complementary symmetry,
Both NPN and
One
PNP.
Both
NPN,
NP and
one
PNP
is
transistors
NPN,
are
another
used.
one is PNP. For the normal push-pull, we have to use both either NPN or PNP. In complementary symmetry, we have to use either one is NPN, another one is
PNP.
PNP.
Push-pull class B is having transformer or not?
Present, sir. In the
Present.
push-pull.
For complementary symmetry,
No, sir.
There is no requirement.
so it is a transformer-less circuit.
Yes, sir.
Which circuit is cost? Cost is high.
Push-pull.
Push-pull,
Push-pull
sir.
Cost is high. Complementary symmetry,
Less cost compared
Less
to
cost.
push-pull.
less cost. Dual power supply is required for which type?
Complementary, sir.
Complementary symmetry. For push-pull class B, which is not required. Hello?
Yes, sir. Not
Yes, sir.
required.
Okay. Frequency response is poor. For which type?
Push-pull, sir.
Push-pull. For complementary symmetry, which is improved.
It is improved.
So, I think all of you understood.
Yes, sir.
Yes, sir.
All of you understood the both types of normal push-pull and complementary symmetry push-pull.
Complement.
Yes, it just do one thing. You are confusing for push-pull and symmetry, complementary symmetry push-pull, right? Hello? Hello?
Sir.
Yes.
So do one thing. Transformer push-pull, amplifier, consider that one. For the second one is transformerless complementary symmetry push-pull amplifier. Okay.
Yes, sir.
You just classify like that. Then you can reduce the confusion, to avoid the confusion. Need not to be worried.
Okay, sir.
Okay, sir.
So you just write it as transformer based push-pull amplifier as first one, normal one. For the second one, transformerless
Complementary push-pull amplifier.
symmetry push-pull amplifier. All of you understood?
Yes,
sir.
sir.
Yes, sir.
Okay. Mostly in one or two classes, we will conclude the third unit. Okay.
Okay, sir.
Okay, sir.
Okay, sir.
All of you submitted your assignments.
Yes, sir.
Submitted.
Yes, sir.
Yes, sir.
Still, I am getting the requests. Please, people, you have to join early. I have mentioned that I think we created the Edmodo class when the hybrid classes are going on, right?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
From the past 3 days also, I am getting the request from the people.